Well, today's discussion about NASA's InSight lander. Before InSight touched down on Mars in 2018, rovers and orbiters mainly focused on the surface of the planet. Now, InSight is giving scientists the first look at the heart of Mars, with 3 new studies about its crust, mantle, and core published just this week. The InSight team members joining us today are Mark Panning of NASA's Jet Propulsion Laboratory, Sabine Stanley of Johns Hopkins University, and Amir Khan of ETH Zurich and the University of Zurich. And I'm your host, Raquel Villanueva. You can use the Ask NASA hashtag on Facebook, YouTube, and Twitter to ask the team any questions. Now, before we get to findings, Mark, can you give us a quick recap of InSight's mission for those who aren't really familiar with the lander?
Yeah, thanks, Raquel. If you bring up image 1, you can see that InSight's a lander. We're not a rover. We're not moving around. We're standing still so that we can record the things we want to record. And we landed with a bunch of instruments that are aimed at, as Raquel said, looking at the inside of Mars rather than the surface of Mars. And we're the first mission that's really focused on understanding the interior of Mars. We landed with a lot of instruments, as I said, but today we're only going to be talking about results from the seismometer, which in the image you could see is sitting out in front of the lander underneath that thing that kind of looks like an upside down pie plate. And as I said, we're trying to understand the inside of Mars, and the plan there, the goal is to understand the inside so that we can look at the formation and evolution of Mars. And the overall reason why we want to do that is because Mars is one of our 4 rocky planets of the solar system, which also includes Earth, Venus, and Mercury. And by going from cartoon understanding of what the inside of Mars looks like to putting real numbers on it, as we've done in the studies that came out this week, we are able to really expand the family tree of understanding how these rocky planets form and how they're similar and how they're different.
It's good to hear our family tree is now growing. Now, before we get to additional questions, I want to ask each of you the same question. What was one of the most intriguing results for you personally? Can we start with Amir?
Thanks, Raquel. You know what? That's a really difficult question, actually, simply because we have made so many interesting discoveries. But if I have to single out one thing, then it would have to be the observation that we have actually, we have landed an entire geophysical laboratory, including a highly sensitive seismometer on the surface of Mars. And that seismometer has actually been able to detect Mars quakes, which have allowed us to look inside the planet, and from which we have learned quite a bit about its interior. For example, InSight has confirmed our view that Mars is a planet that was once probably completely molten, as a result of which it separated into a crust, a mantle, and a core. That's what we see on this image here. And the most fascinating thing is that we have now been able to put numbers on these units, crust, mantle, and core, with the data that we have gotten from InSight. We know the crustal thickness, we know the thickness of the mantle, and we know the core size, and its density, its mass, and of course their properties. And all of this is really what we need in order for us to move on to what I would call the next stage, which is to say something about how Mars formed and evolved, which is really the main reason why we put Mars on the planet in the first place. I think this is, to me, the most single outstanding thing, also because it paves the way for, future missions, future seismological missions, be it single station, because we know it works.
That is fascinating. And what about you, Sabine?
Thanks, Raquel. So for me, I think this would have to be the fact that the core is actually quite large. It's on the high end of what we expected before the mission. And the density of the core is actually on the low end of what we expected before the mission. So the reason those are interesting is because there are big implications for how Mars created its magnetic field long ago. So today, on the surface of Mars, we see that the crustal rocks, some of them are magnetized, and they're magnetized because they formed while Mars had an active dynamo, and that happened over 3.5 billion years ago. But now that we know the size of the core and we have some information about the composition of the core from the density measurements, we can start thinking about how Mars's dynamo worked. And that's exciting because a global magnetic field that was created by the dynamo, that has important implications for Mars's atmosphere. And as soon as you start mentioning atmospheres, you start connecting to whether or not Mars was habitable in its early life.
Habitability is on everyone's mind when you talk about Mars. And Mark, what about you?
Yeah, to me, what's actually most fascinating is what we've done with events that are actually pretty small. The biggest events that we're talking about and that we've used to nail down the details of the crust, mantle, and core in the studies that came out, the biggest ones have been less than magnitude 4. And so these are the kind of events that here in California, where I'm at, there's a good chance you wouldn't even feel it unless you were pretty close to it. And so, the fact that we've been able to get all these details is really interesting. And the fact that these events are all more than 1,000 miles away and we've still been able to measure them is something we could only do on Mars and not on Earth. And that's because on Earth, the background is noisy, and it's because of the oceans. The oceans are always pounding, and even if you're sitting in the middle of Siberia, well away from any oceans, you're always hearing the noise of the oceans. On Mars, you're not hearing that at all because there's no oceans. And that means that in the frequency band that we're looking at, where we're making these measurements, Mars is probably 2 orders of magnitude quieter than anywhere on Earth. And so we've been able to make some really astounding measurements and really get at the things we wanted to do with this mission with events that are actually pretty small.
Which makes me wonder about the core. Amir, you study the core. How does studying it help scientists understand the formation of the planet?
Well, Raquel, the core is really the heart of the planet, so to speak, because it contains the clues to Mars formation. It informs us about the how and when and of what did Mars form. Mars, like Earth, heated up as it formed from the dust and the larger clumps of material that was around in the early solar system. And over the next few million years, the planet sort of separated into a crust, mantle, and core, which is what we saw on image 2 here, please. And this observation tells us that Mars was most likely completely molten for it to form such a large iron-nickel core, as the heavy stuff would, sink relatively easily toward the center of the planet. That's the how. Next, we've learned from InSight that the density of the core, that is the mass of the core, is low compared to what we'd expect if it was made of iron nickel only. This implies that the core of Mars must contain a lot of light elements such as sulfur and carbon and oxygen and hydrogen, because that's the only way to make a heavy iron nickel core lighter. Now, this in turn suggests that Mars probably formed while the dust in the early solar system, which basically consists of a lot of these light elements, was still around. And that suggests again that Mars must have formed right at the start of the solar system. That's the when. As for the what is Mars made, it seems very difficult to form Mars from the same material as the Earth. The need for these light elements almost begs for material that is further from the sun, because the material would bring with it more of the light elements that we need to lower the mass of the core. And incidentally, these light elements in the core also explains why the core of Mars is liquid today, simply because the light elements lower the freezing point of the liquid or of the iron nickel core, like the freezing of water is lowered when you mix it with salt, for example.
Some great details about the core. Now, Sabine, what are the similarities and differences in how Earth and Mars work?
Yeah, great question, Raquel. So we can look at image 3 now. So you can see in the image, Mars is about half the size of Earth. And in some ways, the planets actually behave very differently. So the outer rigid layer of rocky planets, that's called the lithosphere. And on Earth, the lithosphere is kind of thin, and it's broken up into plates marked with these lines here. Now, those plates move relative to each other. That's known as plate tectonics. And it's the motion of these plates that's largely responsible for most of the earthquakes. So, for example, on the west coast of the US, you know about the San Andreas Fault, which is a boundary between two plates that are moving against each other, and that causes lots of earthquakes. There are also strong earthquakes at subduction zones. That's where one plate descends back into the mantle underneath another. That example, for example, happens around the Pacific Rim. Now, because Mars is smaller, it has a thicker lithosphere, and it's much harder to get the surface to break apart and descend back into the planet. That means Mars doesn't have plate tectonics. Mars is a one-plate planet. So we don't expect Mars quakes to be as large or as frequent as earthquakes. And that's how the planets are actually quite different.
It's fascinating to think of Mars as a one-plate planet. And kind of speaking about quakes, Mark, can you tell us what tools InSight uses to detect Mars quakes?
Yeah, thanks, Raquel. So the instrument we're using for these studies is called the Very Broadband Seismometer. and it's supplied by the French. And the image you see on the screen here, image 5, that's a kind of a cross section of what this is, and there's a lot of complicated things happening in there, but there's layers, and the outer layers are all about protecting the instrument from wind and thermal noise, temperature changes, all of that cause noise in the seismometer. And the seismometer itself is deep in the middle of it, some of the kind of complicated metal bits there in the middle. And this is an extremely sensitive instrument. It's capable of measuring motions that are the scale of a hydrogen atom. So this is amazingly sensitive that we can do, and we need to do that because, like I said, these are small events that we're measuring from more than 1,000 miles away. So we need to have that really sensitive instrument. And if you go to image 4, you can see the seismo on the left. You can see the seismometer there in its native habitat on the surface of Mars, making its measurements. And the measurements we get back look like the what we call the seismogram on the right. They're just wiggles showing the ground motion up and down, side to side. And you can see there's 2 big peaks on there. Those are the P and S waves for those who have studied intro seismology or intro geology at some point. And the studies that we're talking about this week are all taking really smaller wiggles that are after those big arrivals in order to get at the structure of the deep interior of Mars.
And I have one more question about those wiggles. Sabine, where are most quakes coming from on Mars?
Yeah, great question, Raquel. So we can actually look at image 6 now. So most of the quakes we've observed appear to come from one region of Mars, and it's called Cerberus Fossae. And this region's about 1,000 miles east of the InSight lander. Now, the fossae occur because forces are kind of pulling the crust apart a bit there, and that's causing the cracks that we see. Now, before the mission, we thought this region might actually be tectonically active and have things like earthquakes because of the shifting and cracking that we were expecting. And we thought this because we've actually seen trails left from boulders that are rolling down the sides of the cliffs. That's what's shown in this image here. There are also signs that this region was actually volcanically active quite recently, maybe tens of thousands to millions of years ago, which for geology, that's quite recent. Now, there's another region of Mars that we thought we might see Mars quakes from, and that's Tharsis. Tharsis is that giant volcanic province that has all the really big volcanoes on Mars. And it turns out, now that we've actually narrowed down the size of the core and we know that it's quite big, it makes sense that we haven't identified any quakes from there. And that's because Tharsis ends up in a region called the shadow zone of the InSight seismometer. So this is a region where we actually can't detect seismic waves if a Mars quake occurs near Tharsis, because the material properties of Mars's mantle cause all the waves to deflect away from the InSight lander. So it's not surprising now that we haven't yet seen any quakes from the Tharsis region, even though we expect it might be tectonically active.
This is kind of a great segue into viewer questions that we have. Now, if anyone watching has a question they'd like to ask, they can use the Ask NASA hashtag to submit it. And first up, we have Fred on Facebook who asks, how does the recorded Martian seismic activity compare with Earth's? Mark, would you like to take that?
Yeah, sure. As Sabine pointed out earlier, Earth has plate tectonics, and that causes really big earthquakes that happen, particularly in places like subduction zones, where the plate's running under another one. Mars doesn't have that, so we don't see any of the big quakes. If you look at the total amount of quakes we see, it's quite a bit less than we see even in the quiet inner portions of the plates that aren't near the edges. We're seeing less seismicity than that. But we are seeing a little more seismicity than we saw on the moon with Apollo seismometers. And so overall, it's a pretty small number. And at this point, as I said, we haven't seen anything bigger than a magnitude 4, whereas on Earth, you get events that are bigger than magnitude 8 or 9. And if you don't know how magnitude scales work, that's a really, really big difference in energy. So Mars is much, much quieter than Earth.
And then we have another one that seems kind of fun. What about meteorites? Robert on Twitter asks, can you detect meteor strikes, and how do you differentiate them from a quake? Mark, would you want to take that one too?
Yeah, I want to dominate all the answers here, but going into the mission, we had hoped to see meteor strikes, see impacts. Those are the kinds of things you can detect. If you look on the moon, we actually detected a lot of impacts with Apollo seismometers. At this point, we have not conclusively seen any impacts, and that's a little disappointing. But the impact rates not very high, and Mars does have a thin atmosphere that filters out some of the impacts. So at this point, we haven't seen one, but that doesn't mean we can't. We have estimations of all sorts of things, and we're actually looking at images from various orbiters around Mars that are always looking for fresh impact craters by comparing images. And whenever any of those are seen, we try to see if we can see it in the data. So thus far we haven't, but trust me, we're looking very closely.
We'll see one day. And Ciencia News. Oh, Amir, would you like to add something?
Yeah. I just wanted to say, I mean, like, just to pick up on Mark's last point, I mean, it's like, so we see these images, right? And we can see that, there's been an impact, since the orbiter was there the last time. So you have the problem is you have a time frame of, anything from half to a full year, and you have to go back and look at the data, or you have to look through the data for that period. And it's like literally like looking for the needle in a haystack to find that thing. But technically, it could be in there, right? It could be in there. But like Mark says, most of the meteorite impacts that we have seen on these images are relatively small, as a result of which you are not expecting to pick them up by InSight. But they could be there.
And then I do actually have another question for you that's coming in. Ciencia News on YouTube asks, what's the biggest surprise about the interior of Mars?
That's for me?
That's for you.
Oh, thanks, Raquel. The biggest surprise, I think, Sabine went over it a little bit. I think, one of the things that I find the most surprising is this. I mean, we sort of had a good idea about, the core of Mars being relatively big, but we didn't expect it maybe to be so big as it is. And as a result of the size, the radius of this thing being, more than 1,800 kilometers, the density, that is the total mass divided by the volume, if you want, is relatively low, as Sabine said. And as I pointed out in my talk about the formation of Mars, it tells us that, the core of Mars has to have these bunch of light elements in there. So that's, I think, for me, as personally, is one of the most intriguing things that we have to understand. It's not something that's just going to be, very simple and easy and straightforward to come up with an answer to this thing. But it does tell us something about the composition of the core of Mars, which again tells us something about how Mars formed, particularly as to, the timing. It has had to have formed very early to have these light elements.
Thanks, Amir. And then Sabine, would you like to add to that?
I agree with Amir completely. To me, that was very surprising. And it's kind of funny because I'm someone who studies how magnetic fields are generated. And I really kind of wanted the core to be a little bit smaller and a little bit more dense, because that actually makes it easier for the planet to generate a magnetic field early on. So now that we know this information, we have to kind of go back and revise what we thought about how Mars's dynamo could have worked and generated that field early on in its history. So I find that very exciting.
Great. We have lots of social media questions coming in. Another one is Neil on YouTube, who asks, will the geologic ages of Mars need to be updated based on your findings? Mark is thinking about that. Would you like to take a shot at the question?
I mean, I think, when the remote observational geologists have done a lot of really careful work with crater counting, and all of that's still applicable. I don't think we've changed that story of what the surface of Mars is doing. That's all still the same. This, as Amir pointed out, this may have some impact in understanding what happened very early, right in formation of Mars, but that's mainly not preserved on the surface because Mars was molten then, and so the surface wasn't there yet. Yeah, I don't think the geology picture has changed. They've done some amazing work with what they can do with remote observation.
Great. And then Partosh on YouTube asks, if there are no tectonic plates on Mars, how was Olympus Mons created and active?
So I can start on that one. So on Earth, others might chime in. So the short answer is it's not fully understood, right? But what we do know is that on Earth, there are different kinds of volcanoes. So you have the kinds of volcanoes that occur near subduction zones where one plate is going underneath another that melts some of the crust underneath and creates volcanoes. But we also have volcanoes kind of in the middle of plates, and they're due to something called hotspots. So a hotspot, Hawaii is a great example of a hotspot volcano. So what happens on a hotspot is you have a plume of hot material coming through the mantle, and that gets to the surface and eventually leads to volcanic activity. Now, because Mars is a one-plate planet, if it has a hotspot, that hotspot would kind of stay in the same location under the surface, which means that you can actually create much bigger volcanoes over it. On Earth, because the plates are moving, it's almost like your surface part of the volcano moves away from where the hotspot is, and so you get a chain of volcanoes instead. So it's thought that probably a region like Tharsis got so big and so volcanic because a hotspot got to stay kind of under one spot for a long time. I don't know if Amir or Mark want to add to that.
No, I think that's.
I would just add that it's absolutely correct. But I'd add in that one of the interesting open questions that we still don't understand is why a hotspot would stay there for billions of years to create the Olympus Mons and the Tharsis volcanoes that seem like they've been active pretty much over the entire history of Mars that's recorded. So that's something that we'd all still like to understand.
I could
That
maybe
was a
add
great
to
question that came in. Okay, go ahead.
Yeah, I could just maybe add that there has been ideas that this plume that Sabine was talking about has been fed by the lower mantle. Like on Earth, we have plumes that originate from deep down, almost at the core mantle boundary of the Earth, and that was sort of has been taken over and has been one of the main ideas. But actually, what's happened now because of the new results of InSight is that Mars doesn't have a lower mantle. It doesn't have the equivalent of the lower mantle of the Earth. So, that idea has to be, it doesn't work. And which is, like Sabine was saying, we need to go back and look at this problem again.
We also have a question coming in about the crust. Kim on Facebook asks, do we know what causes the cracking of the crust?
Yeah, so
Mark,
I mean, yeah, I could talk a little bit. Even if you don't have plate tectonics, planets still have tectonics in the sense of they crack and deform as things happen, and so there are some really long, slow processes that are happening. So it turns out, most of what planets do, you can think about understanding it by what heat in the planet is doing. And so on Mars, like every planet, it's constantly losing heat out to out to space. And that means it's slowly cooling down over time. And when you cool things down, they actually shrink. And that causes a long, slow buildup of pressure because it's shrinking, and that causes cracking. And then also you've got these hot spots underneath that are causing great big volcanoes. Those are great big, huge masses of rock sitting on top of the crust that push down on the crust and cause all sorts of gravitational things at long distances away from big mountains like Olympus Mons and Tharsis. And so, there are still all these forces that are happening, even though we don't have this pretty plate tectonics where everything's lining up in nice boundaries. There's still tectonics happening because of the processes that are happening as Mars is getting rid of its heat.
Thanks, Mark. We have a lot of questions, like I said, coming in. So now we have Lofty on Facebook who asks, has the data given you clearly defined boundaries / sizes to the crust, mantle, and core. Mark, Amir, who would like to take that?
Yeah, I can take a first step at it, and then maybe Mark can follow up. So yeah, I mean, we got some pretty good numbers of say the crustal thickness, but again, it's beneath InSight. It's at one single location. Of course, you can make inferences about locations elsewhere, but you have to make certain assumptions. But we do, I mean, we got some pretty good numbers now that allow us to really, crustal thickness is constrained to within 20 kilometers, depending on certain assumptions. And we know to good, the core, the size of the core, as we said, is pretty well resolved to, 40 kilometers. And therefore, we also know the thickness of the mantle, and we all, we know the properties of the different, the properties, the waves, the speed with which the waves travel through these different regions, the crust, mantle, and core, to a reasonable extent now, and that's, as we said before, is what we need in order to move on from here.
Yeah, and to be even more specific, we now can say the core has a radius of 1,830 kilometers, plus or minus 40 kilometers. We put specific numbers, and the crust is a little bit more difficult because it varies from place to place. But by comparing with gravity, we can make an estimate of the range of possible average crustal thickness, and it's, I believe, 36 to 72 kilometers, I think was what we said. And the interesting thing about both of those is how they compare with expectations. And we've repeated over and over again that the core is at the big end of what we expected. The crust actually tends towards the thinner end of the pre-mission expectations, and excluded some models that suggested that the crust should be over 100 kilometers thick, which also implied a really dense crust that matched the estimations of surface chemistry, and then you extrapolate that down, you get how dense the whole crust is. Because it's on the thin end, we know that the crust is actually is less dense than you'd get just from looking at the surface material. So you probably have to have quite a bit of things like broken up porosity in the top several kilometers of the Martian crust. And so, the new knowledge we have compared with our pre-mission expectations are telling us new things about what's happening with Mars.
And we have several questions coming in about quakes. Nova Tassi on Twitter asks, what power does quakes have? Would a person be able to hear or feel them if they were there? Mark, would you like to start, and we'll give everyone else a chance to chime in?
As a quick answer, if you were standing right next to InSight, at the lander, you wouldn't feel any of these. These are really tiny motions that we're seeing. So you wouldn't have felt a thing. You wouldn't have heard a thing. You would have to look at the seismometer to know what had happened. But the biggest events, magnitude 3.8-ish. If you were right there at Cerberus Fossae, where we think these events have happened, you'd probably feel it. That's a decent sized quake. So if you were right there where the quake happened, yes, but at the location of InSight, no, you wouldn't feel it.
Anyone else want to chime in before I get to the next question? All right, we have Jason Red on Twitter who asks, why does Mars have such a weak magnetic field even with a molten core? Would you like to start, Sabine?
Sure. Yeah, I love that question. So today, Mars does not have a dynamo. The dynamo shut down very early in Mars's history. And that's expected because you kind of need a planet needs to be able to cool very quickly in order to generate a dynamo, in order to create motions in the core, these churning motions that can bend and twist magnetic field lines and create new ones. So Mars is a smaller planet, and now that we know information about the composition, we also learn that it can't really cool as quickly as it needs to today in order to generate a dynamo. But there was a dynamo very early on in the history. The planet could cool faster. And there are remnants of that dynamo kind of frozen into rocks in the crust of the planet. Now, those crustal magnetic signatures are actually, we can measure them today. So That's what we say. That's what we see today when we talk about the magnetic field of Mars today. It's the rocks, the magnetic fields from those rocks that froze in the magnetic field of Mars. So there are still weak fields, and by weak we mean compared to, say, the field strength at the surface of the Earth today, right? Earth has a dynamo, today, and it's creating an active magnetic field. So that field is much stronger. Mars's is weaker because there's no dynamo today.
And we actually have some questions coming in about your backgrounds. We want to know, how did you get your career? Nightman on YouTube is asking, how did you start your career? And how did you get into analyzing quakes on another planet? So I'll give everyone a chance to answer. We can start with Amir, Sabine, and then Mark.
Okay, I studied geophysics, and actually as part of my PhD thesis, I happened to study the quakes from the moon. So that's how I did not start I have a physics background, and I came into this field of geophysics a little by happenstance. And the first thing I was confronted with were these very strange lunar or quakes from the moon, which are extremely noisy. If you the data from Mars, the seismic data from Mars, are really contain a lot more information than the quakes from the moon. So that was my take into planetary seismology, if you want.
Sabine?
Yeah, so for me, my background is also in physics, also in astronomy. That's what I did in my undergrad, and I really got interested in planets probably from watching Star Trek as a kid, to be honest. Next Generation, that was sort of my big inspiration. But because I'm someone who studies magnetic fields, I'm interested in kind of all the planets that have magnetic fields, and Mars is a really interesting magnetic planet, so I love spending time thinking about Mars, and the InSight mission was really a great opportunity for me to get to work with a group of scientists who have so many different expertise in studying the interior of a planet, which is really kind of what I love to do, is trying to figure out what's going on way deep down inside the planet. So that's how I got involved.
Yeah,
Mark?
Yeah, so I started, unlike the other two, my initial background was actually geology. And I started in geology, but I was also kind of good at math. So I wandered off into seismology. And when I did my PhD, I mainly focused on the Earth. I was looking at understanding what's happening in the Earth's mantle. But right after finishing my degree, I stumbled on some funding that was to make up what seismology might look like on Europa, which is a moon of Jupiter. It was funded through a mission that never flew, but I got a chance to think about what seismograms on another planet might look like. And it's been something I've constantly kept working on. And eventually, 4 years ago, I moved to JPL, and that's all I think about now is thinking about seismology on other planets. And that's Mars, that's the moon, that's Europa, Titan, a moon of Saturn, all of these things. I love to think about what quakes look like there and how they look different than what we see on Earth.
It's great to hear all your different career paths to get here. And I actually have another question for you, Mark. We have Samuel on LinkedIn who asks, can you estimate how old the quakes are and if more might happen in the near future?
Well, I'm not sure what you mean by how old. So all the quakes we're seeing are things that are happening right now. So this is, I think sometimes people think of Mars as old. When you look at the surface of Mars, everything is billions of years old or millions of years old. And so you think of it as old. But, what we're seeing right now is activity that's happening right now. This is stuff that's happening primarily under an area that we know had volcanism in the past million years or so. We don't know exactly, but that means that there's activity happening there right now. So we're seeing quakes that are happening right now. And I forgot the second part of the question.
Let me pull it back up. Could we detect more can we kind of see if more can happen in the near future? Can we predict it?
Yeah, so, we can look at the statistics of what's already happened. And so we've seen lots of quakes. More than 700 quakes have been observed already. And so we're going to keep seeing those. Those are happening. We're actually in a really good time to listen right now because Mars' atmosphere is really quiet during this time of year, and so we can detect a lot of quakes, and so we're detecting them every day. As far as what kinds we're going to see, we'll probably see a lot that are pretty similar to what we've already seen. But if you look at the statistics, it's possible we'll see some bigger events. Where, fingers crossed, we would love to see some bigger events.
And we have a follow-up question for Amir. Alyssa on Twitter asks, can Amir explain in a little bit more detail why the light elements in the core suggest Mars formed perhaps earlier than Earth?
Well, that has something to do with the fact that you got to, when Mars formed due to clumping together of material, you have to ensure that you get a lot of these light elements into your into the planet, accumulated or accreted into the planet, which is for Mars. The constraint is really how do you get into such a little planet at the location where it's at? How can you really how can we really explain? I mean, we have to be careful because, of course, the Earth's core also contains, light elements, but they are slightly different light elements than those from Mars. And, the problem is, again, this number, this mean core density that we're getting at is so low, or is relatively low, that you need a lot of these extremely light elements, such as carbon, oxygen, and particularly hydrogen. And those elements, they only stick around the solar nebula, very early, at the very earliest stages of planetary formation in the inner solar system. Because after a couple million years, what happens is that the young sun gets very active, and this solar nebula, this gaseous solar nebula, this gaseous material gets dispersed into the outer reaches of the solar system, right? And then this stuff is gone. And when this stuff is gone, you're not gonna you can't get it into, let alone on the planet, you're not gonna get it into the core of the planet, right? So that's why it has, the constraint that it has to have formed very early.
And Sabine, do you have anything you'd like to add too?
No, I thought that was great.
It was a great answer. Now we have a question coming in about the studies. Dan on Twitter asks, findings say the crust of Mars is likely highly enriched in radioactive elements that help to heat this layer at the expense of the interior. What radioactive elements are likely? How do you detect that? And why are they at the expense of interior? I can repeat that. I know that was a lot to...
Amir, you want to talk about it, or I can talk about it too, but
I don't know. In any case, I would have to have the question again, please, Raquel.
Yes, of course. Findings say the crust of Mars is likely highly enriched in radioactive elements that help heat this layer at the expense of the interior. What radioactive elements are likely? How do you detect that? And why are they at the expense of the interior?
Okay. So the main radioactive elements we have on the crust would be uranium, thorium, and potassium, and that's the same on Earth and pretty much the same on all terrestrial planets. We say that they are enriched because we have, prior to InSight landing on Mars, we had this, there was this previous, in the early 2000s, this Mars Global Surveyor satellite mission that was orbiting Mars and was measuring. It contained a so-called gamma ray spectrometer, which basically measures the number of gamma rays that are emitted from the surface, and gamma rays are emitted from radioactive decay of these radioactive elements, right? So prior to InSight, we had this idea of the radioactive element content, but of course only on the surface, right? And now what we did with InSight is, of course, to you look inside the planet, you look inside the crust. So again, we have to be aware that InSight doesn't directly see radioactive elements. InSight is all about seismology. But you can indirectly estimate from the seismic data and from the models we produced by, running so-called, models that sort of try to mimic the evolution of Mars over 4.5 billion years, right? And what you end up with when you run these so-called evolution models over 4.5 billion years, you end up with something today, which is, the models will predict a crustal thickness. It will predict a lithospheric thickness, and it will predict temperatures. And those things from these modeling studies you can compare with what we have predicted from InSight. And when you do that, you find that, in order to predict the crustal thickness that InSight has seen and the lithospheric thickness, the crust of Mars needs to be enriched in these light elements. If not, you don't get the right, crustal thickness and lithospheric thickness and temperature and stuff like that. So relative to what we had, what we knew, from the surface from this Mars Global Surveyor, the radioactive elements have to be, there are more of them, right? But that means, you can't just get rid of MGS, because MGS actually measured something on the surface. But it means that, as you inside the crust, deeper down in the crust, you have rocks, different type of rocks from the surface that contain more radioactive elements, right? That contain different,
It's a
Yeah,
great
and
breakdown.
the
Go
key
ahead, Mark.
element there is that there's, we have estimates of how much of these heat producing elements were available to Mars based on estimates of the solar material that created Mars. And so if you're putting more in the crust, it means you're taking more out of the mantle. So this, when you melt the mantle to create the crust, you are shoving those heat producing elements into the crust, and therefore relatively cooling down the mantle. So you don't have as much heat production in the mantle. So that makes the mantle a little more cool, gives you a thicker lithosphere, all of that, because we're putting all of those heat producing elements in the crust.
maybe I could
And we
just
have
add one thing to what, maybe I could just add
absolutely.
just a
Go
final
ahead.
thing is that's just to follow up to what Mark said. I mean, and the real way to get at the how many radioactive or the radioactive element content of the crust would have been to put that heat flow probe on there, which we did, but unfortunately it never reached the depths that it had to in order to measure the heat flow that we would have needed in order to put constraints on the radioactive element content of the Martian crust and the heat flow and everything beneath it, really. So that was a very unfortunate occurrence that it didn't function, of course.
But I'd like to thank you and Mark for that really detailed answer to the question. We are getting some great conversations going, and we have Niels on YouTube who is asking, are any of InSight's findings likely to influence the science mission of Perseverance or future Mars missions? Mark, would you like to try?
Yeah, Perseverance is sampling surface material, and we're not directly affecting that. We're looking deep inside, and the deep inside isn't at the surface. So Perseverance is going to make their decisions on what to sample at the surface based on orbital observations and what they see as they drive around. And so we're not going to probably have any direct impact on Perseverance necessarily. But in terms of future missions, things we'd like to see on Mars, so Amir just pointed out, we'd still love to get a heat flow measurement. That would be a great future mission, and we now know more about where quakes happen near InSight. But as Sabine said, there's also likely to be seismicity associated with Tharsis. So we can imagine putting seismometers in different places on the surface, and we're constraining better where we'd like to do that in order to better increase our understanding of Mars.
And if I can add just a little bit to that, even though a lot of the basis of the mission and the focus of the mission is the seismicity and understanding the deep interior. There are instruments on InSight that look at the surface and look at the atmosphere. So we have cameras that can tell us about the surface, and that helps us understand the geology and how things, what's the very, very top layer of the surface, what's it all about. And even though we're learning that from the InSight lander location, that's one data point, but it's an important data point to try and understand all of Mars. And we learn about the atmosphere of Mars. It turns out to be important to kind of take out the atmospheric signals from the seismicity signals. And that, again, can kind of be used with all the atmospheric information we have on Mars. And all of that's going to be helpful for any mission to the surface of Mars in the future.
We do have time for a couple more questions. So we have Jesse on Facebook who asks, scientists believed the factors like the moon's gravitational push and pull, the planet compressing, or meteor impacts caused quakes. How likely is it that more than one factor could be causing Mars quakes?
I mean, I can talk about that briefly. I mean, quakes are an expression of stresses and forces within the crust of Mars, and undoubtedly that those stresses are the combination of lots of different things. I got at that earlier with talking about the overall slow cooling and the weight of big things sitting on the surface of Mars, and that's even including weight of the ice caps at the North and South Pole. All of those things are putting pressures on Mars and changing the stress within the crust. So everything is a combination. There's no one single answer to what's causing the quakes.
Maybe I could just add, I mean, it's true that for the moon, we found these so-called deep moon quakes, which were, apparently they correlated very well with the tides that were raised on the moon by the Earth. And I suppose the question is a little bit the same here. Could, the Martian moons influence Marsquake activity? But that's actually pretty simple to answer, and not me personally, but people have looked at correlations between the tides raised by Phobos. I mean, Deimos is too far away and it's too small to raise any significant tides on Mars. Phobos does raise a tide, but it wouldn't be strong enough to produce any strong quakes or stresses in the crustal lithosphere or the interior of the planet that would, release any type of or produce any type of seismicity as we see it. At least we haven't seen that yet.
Mm-hmm. And we have time for two more questions. So Sonia on Facebook asks, what's the mission going to look at next?
Maybe I can take a stab at that. I mean, one of the interesting things with regard to the core, Sabine has been talking a lot about the magnetic field, is of course the question of whether Mars has a solid inner core like the Earth has. Likely it doesn't, but then again, we don't really know, right? We have to go down and dig into the data and look for it. This is very likely going to be a very difficult problem, and another one of those things where you have to look for the needle in the haystack. But if Mars contains, the equivalent of an inner core, then it is in the data, and it's about trying to extract that signal, really. But that would be a major finding.
Mark, Sabina, would you like to add to that?
Go ahead.
So yeah, I agree. I'm most interested in seeing whether or not we're going to get some information about if and how big would a solid inner core be in Mars. And I think that means, we're waiting for bigger earthquakes as Mars quakes as well. That would be very helpful, and from the right location so that we can see them at the InSight lander. So everyone cross your fingers and keep wishing and hope that this happens.
Yeah, and I just say we're continuing to listen. We're recording right now. So we're getting new quakes all the time, and there's still a lot of mysteries about the quakes themselves. The ones we're talking about that we've used for these studies are all a type of quake that we call either low frequency or broadband, and these look a lot like earthquakes in a lot of ways. We have a pretty good understanding of how they work, but there's also different types of quakes we're seeing that are called. We have a whole suite of names for them: high frequency, very high frequency, even super high frequency, and they're all different, and they have lots of weird properties that we don't totally understand. And so, the more of that data we can get and look at the statistics of when they happen and all of that, those are all a lot of questions we'd like to understand. And I don't have a quick answer for you for understanding all of them yet. And hopefully after some more data, we'll have better answers for that sort of stuff.
Well, this is a good segue into our
ad. Oh.
Go ahead.
Sorry. I'll just also quickly add that one thing that's been great about the length of time of the InSight mission is that, so Mars's year is about twice that of Earth's year, the amount of time it takes to go around the sun in its orbit. And so we're also able to now, because we've been there for so long, look for seasonal effects, look for, since we have repeats of the Mars seasons. And so I think that's also an interesting thing we're going to be looking at in the future.
That kind of segues into this final question that I have that I want each of you to quickly answer. Joe on YouTube asks, based on all your findings, what would be the next generation of instruments you would like to see sent to Mars for further understanding? Oh, I see Sabine getting excited about that one. Would you like to go first?
Sure. I think that there is a whole lot of opportunity in things like drones or helicopters, right? We have Ginny there right now. The ability to move around and get information from different places on the surface, that would be really great in terms of learning about the next generation. We want to have information about the magnetic field, the surface properties, the gravity, seismicity. We want it from a lot of different locations. So the more we can do that, the more we're going to learn about the interior of Mars.
I'd like to go next, Mark?
Sure. Yeah. So for me, I 100% agree with Sabine that more at more locations, and connected with that. One of the big challenges we have in InSight is that we're trying to locate events with one station. And, if you took an intro class, they teach you somewhat incorrectly that you need 3 stations to locate a quake. We've proven that you can do a lot with one station, and we can locate quakes with one station. But the fact remains, it's still a lot easier to do a lot of seismology if you have more stations. And so, there are options. You could imagine a global network of stations that are really sensitive and are measuring like what we're doing, and just really nailing down the global picture of what's happening with seismology, and then maybe looking at variations in crustal thickness. Or you could imagine local networks that are looking at areas of interest like Cerberus Fossae or Tharsis, where you could get away with maybe having less sensitive stations because you're sitting right where quakes are active. And so maybe you could have cheap landers with less expensive sensors, and get networks and really get into understanding locations of these small events that we can't really locate with one station and with InSight.
And then Amir?
Yeah, I think I share the optimism of Mark and Sabine, but I think we still have, in the light of what we've learned now and what we've seen with a single station, and we've done a lot with a single station, right? And it's amazing. It's outstanding, the stuff that we've been able to do. But I still think that we have to keep in mind that, we have all of these different, geophysical methods, like you look at magnetic fields and gravity and stuff like that. But, we have to keep in mind that seismology is the gold standard in the sense that it is the geophysical method that has, that gives you the highest resolution when you look inside a planet. And for that reason, we've been talking a lot about, I don't want to make this a long story, but we've been talking a lot about the broadband seismometer, but there was also a short period seismometer on there. which is based on MEMS technology. And it's light, it's compact, it doesn't weigh anything, and you could send stuff like that. But unfortunately, what it's turned out is that a lot of the stuff, the Mars quakes that we've been using to look inside the planet have really only been picked up properly by the broadband seismometer. So I think, going back and doing arrays and, tens of station stuff, of course, we'd love to do that. And we'd like to dream about magnitude 5s and 6s. But, these particular, the seismometer that Mark talked about and he showed on the images, they are built specifically and, in laboratories for these types of missions. And it's not something that's simply, packaged and moved elsewhere, right? So it's a little more difficult than that if you want the type of stuff that we've been able to do on Mars with InSight. But I think, as I said in the beginning, I think the fact that we've been able to do so much with a single station is really is going to pave the way for future missions, because you can just take a single station and move from there. Place it on a different location of the planet, of course, but
we're all dreaming of big
Right.
Mars quakes, like you said. That is all the time we have today. And I'd like to thank everyone for their questions, and thank you to the team for chatting with us today. Now, for more information and to stay up to date with the mission, visit mars.nasa.gov/insight and follow @NASA Insight on Twitter and Facebook. Thanks for watching.